Welcome to a lesson on cryptography and the substitution cipher. When people need to secretly store or communicate messages, they turn to cryptography. Cryptography involves using techniques to obscure a message so outsiders cannot read the message. It is typically split into two steps: encryption, in which the message is obscured, and decryption, in which the original message is recovered from the obscured form. One simple encryption method is called a substitution cipher. A simple example of a substitution cipher is called the Caeser cipher, sometimes called a shift cipher. In this approach, each letter is replaced with a letter some fixed number of positions later in the alphabet. As an example, a Caeser cipher with a shift of 5 right would replace A with F. Notice how F is 5 positions to the right of A. It would replace B with G, C with H, and so on. So the complete cipher, only using the letters in the alphabet, would look like this, where in black we have the original letters, and in red we have the letters they would be mapped to. Let's use the shift of 5 right to encrypt the following message: meet at the bank at 8 a.m. We're asked to write the final code in 4-letter blocks, which is common. We wouldn't want to leave spaces where there are spaces between the words, because that might help solve the encryption. So the first 4 letters are M, E, E, T. So M maps to R, E maps to J, and T maps to Y. So we'll have R, J, J, Y, space. The next 4 letters are A, T, T, H. Then we'll have E, B, A, N. Then we'll have K, A, T, E. Then we'll have I, G, H, T. Then we'll have A, M. So for A, T, T, H, we would have F, Y, Y, M. For EBAN, we'll have J, G. For A, we'll have F, and for N, we'll have S. So FS. Next, we have KATE. So K will map to P. A maps to F. T maps to Y. And E maps to J. Next we have I, GHT. I maps to N. G maps to L. H maps to M. T maps to Y. And then we have AM. A maps to F. And M maps to R. Notice how we're 2 letters short of a 4-letter block. So this is often padded with an extra letter. So let's just use A to complete the block. A. This would be the encryption for the given message using a shift of 5 right. Now we want to decrypt the word RPJHT if it was encrypted using an alphabetic Caesar shift cipher with shift 15, meaning we'd map A to P. So if we map A to P, B would map to Q, C would map to R, D would map to S, and so on. Notice how after K maps to Z, L maps to the first letter in the alphabet, which is A, and so on. Now to decrypt this, we'll look for these letters in the red row, then determine what the original letter was. So here's R, P, J, H, and T. So again, R was originally C, P was originally A, J was originally U, H was originally S, and T was originally E. So the original word was cause. Notice in both of the previous ciphers, the extra part of the alphabet wrapped around to the beginning. Because of this, a handy version of a shift cipher is a cipher disk, such as the Alberti cipher disk shown here from the 1400s. In a cipher disk, the inner wheel could be churned to change the cipher shift. This approach is used for secret decoder rings. The security of a cryptographic method is very important to the person relying on their message being kept secret. The security depends on two factors. Number one, the security of the method being used, and number two, the security of the encryption key used. In the case of a cipher shift, the method is a shift cipher is used, and the encryption key is the specific amount of shift used. Suppose an army is using a shift cipher to send their messages, and one of their officers is captured by their enemy. It is likely that the method and encryption key could become compromised. It is relatively hard to change encryption methods, but relatively easy to change encryption keys. For example, for a shift cipher, we could just change the amount of shift and possibly the direction. During World War II, the Germans' Enigma encryption machines were captured, but having details on the encryption method only slightly helped the Allies, since the encryption keys were still unknown and hard to discover. Ultimately, the security of a message cannot rely on the method being kept secret. It needs to rely on the key being kept secret. The security of an encryption method should depend only on the encryption key being difficult to discover. It is not safe to rely on the encryption method or algorithm being kept secret. A brute force attack is a method for breaking encryption by trying all possible encryption keys. Suppose you intercept a message and you know the sender uses a Caeser cipher, but do not know the shift being used. Let's say the message begins EQZP. How hard would it be to decrypt this message? Since there are only 25 possible shifts, since there is 26 letters in the alphabet, we would only have to try 25 possibilities to see which one produced results that make sense. While that would be tedious, one person could easily do this by hand in a few minutes, and one computer could try all possibilities in under a second. So in this table here below, here are all 25 possibilities for EQZP. Notice how only one of them really makes sense, and that would be a shift of 12 right, which would decrypt to the message send. To make a brute force attack harder, we could make a more complex substitution cipher by using something other than a shift of the alphabet. We could get a more secure cipher with the trade-off that the encryption key is harder to describe. The key would now be the entire mapping rather than just the shift amount. While there are only 25 possible shift cipher keys, 35 if we include the digits 0 through 9, there are about 10 to the 40th power possible substitution ciphers. That's much more than a trillion trillions. It would be essentially impossible, even with supercomputers, to try every possible combination. Having a huge number of possible encryption keys is one important part of key security. There are 35 choices for what A maps to if we use all the letters and the numbers 0 through 9, then 34 choices for what B maps to, and so on. So the total number of possibilities is 35 times 34 times 33, all the way down to times 2 times 1, which should be equal to 35 factorial. Unfortunately, this cipher is still not secure because of a technique called frequency analysis discovered by Arab mathematician Al-Kindi in the 9th century. This shows the common frequency of letters in the English language. It may be hard to see, but notice how E has the highest frequency, followed by T and A, which we can see here in this Pareto chart. So by analyzing the frequency of the letters used in a code, it would make it easier to decrypt the message. I hope you found this lesson helpful.